Each drilling rig, no matter what its size or type, has one simple task, and that task is to connect the Earth's surface to an underground reservoir. To enable the rig to complete this task, there are 5 main components or systems. Each rig consists of 1. A rotating system, 2. A hoisting system, 3. A circulating system, 4. A power system, and 5. A pressure control system. In this drawing, I've labeled each of the 5 main systems with their significant components as you'd see on an operating rig. Let's take a few minutes to orient ourselves to their locations and look at how they fit all together. Once we are familiar with the parts and their locations, we'll describe their functions. Let's start with the rotary system. Within this system, you have the drill bits, the drill collars, the drill pipe, the Kelly bushing, and the rotary table. On more modern rigs, the Kelly and its parts have been replaced by the top drive, also known as the power swivel, and the downhole mud motor for directional drilling. In the hoisting system, you find the derrick, the drill line, the drawworks, the crown, and traveling blocks, and the drilling hook. The circulation system consists of a circulating fluid, usually referred to as mud, the mud pit, the mud pump, the rotary hose, the swivel, the flow line, the shale shaker, and other filtration devices. Between the drill pipe and the borehole wall, there is a space called the annulus that is also part of the circulation system. The power system consists mainly of diesel engines that run electric motors, fuel storage tanks, a compounder made up of pulleys, belts, shafts, gears, and chains, and on some newer rigs, a silicon-controlled rectifier, or SCR. The main component of the pressure control system is the blowout preventer, BOP. Made up of valves, pressure gauges, and chokes, arranged in stacks with a series of rams and preventers, the BOP's principal function is to prevent blowouts. On land rigs, they are usually bolted to the top of the well right above the wellbore, below the derrick floor. On offshore rigs, BOPs are placed on the ocean bottom above the wellbore on the ocean floor. With its own independent power source for safety, the blowout preventer panel with its controls sits right on the derrick floor for easy access. Now that we are familiar with the different components in the 5 systems, let me explain in detail how each of these 5 systems function to make and support the wellbore and drilling process. We'll start with the rotating system. Basically, within the rotating system, the drill bit turns, cutting the rock and making the hole. As the bit rotates, drilling fluid is forced down the drill pipe to jet nozzles in the drill bit as it cuts the rock. These jets of fluid clean the bottom of the hole of the rock debris from the rotating drill by moving the debris away from the bit and then up to the surface. The drill stem rotates the bit. What causes the drill bit to turn? There are 3 ways to turn the drill bit. The first is the conventional rotating system using the rotary table, the Kelly bushing and Kelly. The Kelly is a square or hexagonal shaped 40-foot length of pipe that threads into the drill pipe. A swivel connects the Kelly to the hook. The Kelly is fitted into a square or hexagonal opening in the Kelly bushing, which fits into the rotary table. As the rotary table moves, the Kelly and the Kelly bushing also rotate, thus turning the drill stem and bit below. As I said before, the top of the Kelly is attached to a device called the swivel. Allowing the Kelly to rotate, the swivel provides a passage for the drilling fluid to flow from the surface to the bit below, and also prevents the traveling block and hook from rotating while the drill stem is being turned. Another, newer type of rotating system is called the top drive. The drive shaft, with its powerful hydraulic motor, screws directly into the drill stem. Replacing the Kelly bushing, and the rotary table, the top drive suspends and rotates the drill stem. The drilling fluid flows through the top drive, down through the drill stem, to the bit below, just like with the Kelly assembly. The principal difference between the Kelly assembly and the top drives is that the top drives are superior to the conventional rotating system because they permit circulation and rotation while pulling out of the hole, and they allow 3 stands or 90-foot lengths of pipe to be added at a time rather than the 30-foot. Typically, a top drive can reduce drilling time by about 25%. The downhole mud motor is the third type of rotating system. Used in directional drilling, the mud motor is mounted directly above the bit and is powered by the drilling mud. The drilling mud turns the bit without rotating the drill string. Still used on older rigs, conventional rotating is still used, while more modern rigs are usually equipped with top drives. All rigs engaging in directional or horizontal drilling use the mud motor. To enable the rotating system to work, you must have the basic drill string. Let's talk about the components of a drill string. For all practical purposes, a drill string is a tube of steel pipe with multiple connections that extends from the surface to the bit. In other words, everything in the hole. It has 3 functions. First, it transmits rotational energy from the surface to the bit. Second, it conducts the mud system from the surface to the bit. And third, it puts weight on the bit to maximize its penetration rate. Made up of lengths of 30-foot stands of drill pipe with various diameters that can be screwed together, the drill string has 3 basic configurations. Starting with the drill pipe, which makes up the bulk of the string, a drill bit is attached to the end and is used to break the rock. Next, thick-walled, high-density drill collars are placed above the bit to put weight immediately above it. The Kelly pipe is the topmost joint of the drill string with from 4 to 6 flattened sides and is 40 feet long, 10 feet longer than drill pipe. The Kelly or top drive transfers the torque or rotating power down to the drill string to the bit, allowing the rock to be cut. Let's now examine the drill bit and its colorful history. As I said before, drilling an oil well appears deceptively simple. However, it is quite complex, involving advanced scientific principles of fluid flow, pressure, heat, material design, to name a few. The history of the technological advancements of the bit design is quite fascinating, which have led to the development of the sophisticated drilling bits we use today. Let's take a few minutes to look at that history. When Edwin Drake drilled the first oil well in Titusville, Pennsylvania in 1859, creating the modern petroleum industry, he used technologies that were available at the time. As you know from your history, humans from the dawn of civilization have dug, mined, and drilled into the earth for access to its precious, useful minerals. In China, Iran, Poland, and many other locations throughout the world, humans had already developed quite sophisticated drill bit technologies to extract salt, water, gold, coal, and even oil. In fact, when Drake drilled his first well, he used the tools and machinery that were being used to drill for salt in nearby salt mines in the northeastern part of the United States. He built a derrick from which he strung up rope made from hemp with a cable tool attached at the end. Utilizing generated steam to raise and lower the cable tool, he pounded the ground until a hole formed. Intermittently, he stopped the pounding and then baled out the bits of dirt and broken rock until he had a hole. Repeating this process, he was able to drill a hole 69 feet into the ground before striking oil. The cable tool rig that Drake used was dropped repeatedly onto the ground. It was really quite effective in breaking up rock and dirt so that it could be baled out or removed. Simplistic enough to be powered by human power, the cable tool rig could also be raised and lowered by steam power. Surprisingly, in the early days in Titusville, where money was tight and technology was hard to come by, a man stepping down into the noose of the hemp rope to raise the cable tool bit, it could drill up to 3 feet a day. They were then able to reach the shallow pay zones of many of the early wells in as little as a month. Although effective, the cable tool rig had one major flaw, especially in wells where the oil was trapped under pressure. When the cable tool penetrated into the pay zone, the releasing pressure forced the oil up and out of the well in what is known as a blowout. We've all seen movies showing these dramatic blowouts that sometimes result in death to those nearby, destruction of the wellbore and the environment. Needless to say, technology to prevent or lessen these blowouts had to be developed. As you can imagine, besides the need to reduce or eliminate blowouts, there were other problems with the cable tool drill bits. Operating within a hole dug into the earth in extremely dirty and hot environments, the bits were subject to enormous mechanical stresses which caused them to dull quickly or to break inside the hole. Digging out these broken bits or replacing them wasted rig time and cost a lot of money. The industry needed a better drill bit. Although first invented in France in the 1860s, the first rotary drilling bit was used by Portillo Higgins in 1901 to drill a well that led to the Lucas Gusher blowout, a part of the Texas oil field that later became known as Spindletop. It was shortly after that Howard Hughes Sr. patented a two-coned rotary drilling bit that could revolutionize drilling, because it introduced the hollow drill stem that enabled the broken rocky debris to be washed up and out of the borehole. Although the design has been improved over time, it remains the most popular type of drill bit used today. Let's examine the rotary drill bit to better understand why it quickly replaced the cable tool drill bit. Tricone roller bits are the most commonly used bits. A clockwork rotation of the drill string causes the 3 roller cones to also rotate, bringing successive teeth to grind vertically at the bottom of the hole. With the weight concentrating at the point of the teeth, the rotating bit crushes the rock. The debris from these cuttings are then swept away by the mud jetting out of the 3 downward-facing nozzles. Tricone bits can have teeth milled from hardened steel, or, for harder rock, small tungsten carbide teeth inserted into a steel cone. Regardless of the material used, the teeth eventually wear down and the drilling rate slows, requiring that the drilling bits be replaced. A new improvement in the materials used for drill bits is the polycrystalline diamond cutter, or PDC. They use very hard polycrystalline man-made diamond wafers on the face of protruding bronze bases. They differ from the tricone bits in that since the PDC bits do not have any moving parts and are made from diamonds, they last longer. One bit can sometimes be used to drill an entire well. Like the tricone bits, PDCs rotate, but this bit has a shearing action, while a rotary bit has a crushing action.